Hello and welcome back to the lab. On the bench today, we have another piece of vintage Hewlett-Packard test equipment, the HP 239A oscillator. This particular one seems to suffer from some of the same problems that other pieces of equipment from HP of this vintage also suffer from, and that is the degradation of the plastics, specifically the ones used in the knobs and sometimes the binding posts. They, they tend to develop cracks and crumble and fall apart and break off. And this one suffers from that same problem as well. This one's no exception to that rule. Unfortunately, just the quality of the plastics used in Hewlett Packard parts um, didn't seem to stand up to the test of time. Now, to be to be fair, I think HP probably expected these instruments to have a 10-year useful lifespan, and I'm expecting to get like more like 75 years of useful life out of these instruments. So I'm not really um, being fair, but nonetheless, I do expect to get about 75 years of life out of these old instruments. And so we're going to have to try to do what we can to restore them, even though these knobs are becoming harder and harder to find, because even the ones that you do find also have cracks and they're crumbling and falling apart as well. Um, so we just have to make do with what we can do here. We can see that there are cracks in this knob, and the little plastic dial has broken free from the back. I should be able to glue that up just fine. The plastic dial on this one is not even attached to a knob because that knob has broken off completely. Um, the brass insert that holds the knob to the shaft is still attached, but there is no plastic knob on there. And I think I have a solution for that we can do as well. Um, you can see on this one, there's a tiny crack right in through here. It appears that someone has tried to previously glue this, and that seems to have held. But of course, the plastic dial has broken free again. So I ought to be able to glue this one up as well. Now, this plastic dial, the numbers on the plastic dial, the lettering on the dial itself, most of it has worn off or dissolved off or something, and it's missing. So hopefully I can find a solution to get that stuff printed back on this dial, or find another replacement dial for it. I'm not sure yet. These front knobs, they seem to be okay at this point. Um, the push buttons, they have not really degraded. They seem to be in good enough shape. The output terminals, these banana jack binding post terminals, they often develop cracks and break apart as well, but these seem to be in particularly good condition. Now, I noticed on this instrument it's missing the top trim. The little trim strip that goes in here is missing. I think I have a replacement for that, but even if I don't, I know where to get some, so I can replace that. This one did come with all four plastic feet and the two wire tilt stands, um, which is unusual because often those are missing from the instruments, although they're in good supply and they're easy to find and come across. And they're always in good condition. They don't have the same cracking problem that these other plastics do. Let's take a look at the rear panel of this unit. It's quite simple. We have the standard line cord socket for the input. We have a fuse holder for the line fuse. And if you take a look at it, which I already did, for 120 volts, which is what we use here in the USA, it should be a 1/8 amp fuse. And it turns out that this one is a 1/4 amp fuse, not a 1/8 amp. So this is the wrong fuse. So we have to try to hunt down the correct fuse. I think a 1/4 amp will be okay. We shouldn't experience any difficulties. But it means that at some time the fuse has been replaced, and that might mean that there's a problem internal to the instrument. causing them to replace the fuse. I don't know. Oftentimes, the electronics inside are in perfect shape, and the only problem with these units are the plastics that we already talked about. The line select switch, line voltage selection switch, it is set to 120 volts, so that's good. That's what we use here in this country. Now, right here, there's supposed to be a serial number plate. This serial number plate is missing. The rivets are still there, but the plate itself is missing. So that's a little suspect. I can assure you that I purchased this instrument off of eBay from a reputable seller, but I can't speak to the provenance of this unit before that seller acquired it. So somewhere along the lines, something fishy may have taken place here, but this instrument has no serial number. All right, so that's an overview of the outside of the 239A. I have not um, powered it up or turned it on yet, so I have no idea if it's working. The only thing I've done to this unit so far is clean it thoroughly outside because it was really, really, really dirty. And I actually took the knobs off to clean them up, and then I put them back in the same condition they were originally found in just to demonstrate how they develop cracks and start to fall apart so readily. So what is a 239A? All right, here we see the 239A sitting atop one of my 339A distortion measurement sets that I've done several previous videos on. You can check those out in my channel. The 339A distortion measurement set is really a low distortion oscillator, which is this section of the instrument, combined with a distortion analyzer, which is this section of the instrument. And a device under test is placed between the low distortion amplifier's output over here and the distortion analyzer's input over here. That's how the 339A distortion measurement set is set up. Now, HP realized that not all of their customers may not necessarily want a distortion analyzer, but they might want just the low distortion oscillator portion of the 339A. So HP took the same circuit that was in the 339A in this oscillator section and packaged it up in a separate enclosure and renamed it the 239A. So the 239A oscillator is actually the same exact electrically the exact same circuit that's in the 339A for the oscillator section. So it's a very low distortion audio oscillator. It has a range from 10 hertz up to 110 kilohertz, an output amplitude of 3 volts down to 3 millivolts, and with a step attenuator as well as a variable amplitude control. 600 ohm output impedance with dual banana jack and binding post output terminals. The 239A has push buttons for frequency range selection, whereas the 339A has a rotary switch for that same frequency range selection. That's about the only difference. Other than that, it's the exact same circuit. The oscillator section of the 339A is packaged up in its own enclosure, and they call it the 239A. HP made the 239A from 1979 up until 1983, so about 4 or 5 years of production. In 1979, it sold for $575, so that's a reasonably priced piece of test equipment, especially one from Hewlett Packard. $575 is pretty cheap, actually, even in 1979 dollars. But they only made it for that short range of years, so there really aren't that many of them available. So I was lucky enough to get one. Even though the knobs are falling apart, I was lucky enough to find one up for sale on eBay. So I purchased it. So let's open up the 239 and take a look inside. But before I open up the instrument, I thought I would try to repair some of the cracked knobs and maybe get some of the cosmetic restoration accomplished on this unit. So I took the level control attenuation step attenuator knob, which has a small crack right here where my screwdriver tip is pointing, and I tried to place a drop of super glue in that area and also glue on the clear disc with the numbers on it. In fact, you can see that most of the numbers on this disc have been worn off. Um, I'm not sure if I can repair that one or not, but hopefully that will work for this knob, and that super glue will at least hold it together at least for a little while. Now for the frequency units knob, I put that one also in my vise, and you can see that someone had previously attempted to glue the cracks that are in this knob up here in this area, and that can be seen as like a brownish type glue. I'm not sure what kind of glue that was, but again, I'm going to put a drop of CA glue, super glue in there, and also glue this clear disc with the units numbers on it to this knob, and hopefully that will hold at least for a little while. Now for the frequency tenths knob, the 0 to 0.9, 0.0 to 0.9 numbers knob, that knob was cracked off and completely missing. So all that was left was the brass insert, which I can't really use. So I'm going to take that off and discard it. And what I have is I took this other knob, which actually comes from an HP 5328 frequency counter. All right. And this is a similar knob, although not exactly the same. This knob has the same lever type handle on it, but it also has a pointer indication here, which the correct knob should not have. But we're just going to ignore this pointer and use this knob to work as the frequency tenths knob. And so I'm going to try to take the tenths clear discs with the numbers on it and glue it to the back of the HP 5328 knob, and hopefully we will have a third knob. See here it has a pointer at this point here, which will point to the number 5 or something, I guess. Oh, it looks like it points in between the 0 and then 9. But we're just gonna ignore that because this is the only solution I really have at this point. So I'm going to use this knob, even though it's not the exact correct one. Hopefully it will work well enough. I also had to pop the decorative end out of this knob to allow the concentric shafts to pass through it, because this knob is the rear knob of a dual knob set. There's also a frequency vernier knob that's adjustment that's in the front of this knob. So that's why I had to pop the decorative end off of the HP 5328 knob. Okay, so after a few minutes of drying time, I reattached the knobs to the front panel of the instrument, and you can see that we now have all the knobs intact, at least for the time being. I consider super glue to be a temporary solution to this problem. I haven't really figured out the correct glue to use to do a permanent repair to these uh, plastics, and there probably isn't one. But at least for the time being, if I'm careful with my rotation, I will have all working knobs, and they're attached numerical discs on the rear. Now, also, you can see on this one, there's a pointer that points to the number 5 for no particular reason. Um, that's because this knob doesn't actually belong on this instrument. It goes to a frequency counter, not this particular instrument. But if you just ignore that pointer and look at the number in the window, that number is correct. Also, I have not been able to figure out the best way to replace the missing numbers on the level disc. There used to be some dry transfer numbers you could just emboss, rub onto there and then cover them with a clear coat or something like that. I don't know if those types of things are still available. I'm going to take a look around and see if I can find something like that. Or maybe one of my viewers might have an even better solution to replace the missing numbers on this level disc. But at least the knobs are intact for the time being. Oh, also, I was able to locate a top trim strip for this instrument, so I dropped that in place as well. Now, we can take the top off and take a look at what's going on inside this instrument. So let's do that now. So we remove the two Aussie drive screws at the rear of the instrument. And then I removed 8 additional positive drive screws that hold the inner shield cover on. And this inner shield comes right off. And there's the circuitry inside the instrument. I wanted to make sure that we don't see anything obviously burnt or shorted or anything like that, any kind of unusual stuff. So we'll do a quick visual inspection. Because the incorrect fuse was in the rear panel of the instrument, so perhaps something was wrong. Chances are they just put the incorrect fuse in for no particular good reason. But let's take a look and see. I don't see anything obvious. I wanted to look for exploded electrolytic caps or anything like that. I don't see anything burnt or obviously any visual problems whatsoever. So I'll just go and find the correct fuse and drop it in the fuse holder. Taking a quick look at the circuitry. Of course, we have the push button switches that select the frequency range, 10 hertz, 100 hertz, 1 kilohertz, or 10 kilohertz. They're connected with these strange kind of push rods that are offset because the push buttons are at the top of the instrument, and yet the switches are along the bottom of the instrument. So there's these weird L-shaped or Z-shaped or something arrangements to select the switches and select the correct push buttons. Kind of strange, but it works very well. The frequency vernier pot here, very high quality pot. These mylar capacitors for each frequency range. The circuitry that we're looking at is another one of those Wien bridge oscillator circuits, like I've talked about many times, including the 200 CD, the 204C, and so on and so forth. This is a Wien bridge oscillator circuit. Instead of the light bulb that like the 200 CD uses as its feedback control for amplitude and distortion control. Instruments like the 239A use a FET instead of that light bulb to control the amount of negative feedback to minimize distortion. I believe this component right here, where my finger is pointing, is that FET that we're talking about here. I believe that that's the FET. In fact, it looks like it's the only transistor in the instrument. A couple of op amps. One is for feedback, and one is for to provide gain to sustain oscillation. The main oscillator op amp. We have power supply circuitry in the rear. Of course, it's shielded by a separate shield. It's inside of a small compartment on its own, separated and independent from the rest of the oscillator circuit. Power transformer in the back, again, completely isolated and outside of the inner shield of the instrument for isolation. I don't see anything obviously wrong or failed here, so I think it's safe to plug it in and turn it on and see if it works. It probably does. Let's find out. Again, once you've plugged the instrument in, there's line voltage available inside this instrument. So don't go sticking your fingers back here, or you might be shocked at what you find. That's my little safety warning for today. All right, it's plugged in. Let's turn it on. The lamp on the front panel has lit up. I don't see any output on the screen. Oh, looks like we have a repair to do. I don't see any output. Huh. Okay. Let's poke around a little bit and see what we can see in here. Okay, so when I look at the output terminals on my scope, I see absolutely no signal whatsoever. So I started by checking the power supplies. There's a plus and minus 15 volt power supply test point right inside the enclosure back here. Both those power supply levels are good. The circuit is very simple, so there shouldn't be much to look for. So I put my scope probe on the output of the attenuator switch here, the level output switch that should connect almost directly to the output terminals. Lo and behold, I can see signal. I do have a sine wave there. It seems to be working perfectly fine. So somewhere between the output of the output attenuator and the output terminal itself, there must be an open. There's a disconnect, a broken wire, or something like that. So I'm going to have to take a look, see if I can't find that. I'll come back when I've got that sorted out. So looking at the schematic, when I put my scope probe on this wire right here coming out of the output attenuator, I can see the sine wave signal. When I put my scope probe on the output terminal itself, I do not see the signal. There's only one thing in between here, and that is a fuse. F1, 0.062 amp fuse. Someone has obviously at some time in the past shorted the output to ground, blowing the fuse, and that's why we don't see any signal at the output now. I'm not so sure I can find a replacement for this fuse. I might have to just jumper it with a wire and take my chances, since I'm not going to be shorting the output. Um, and in the meantime, I'll take a look for a fuse, but I'll just stick a wire in there, and we'll get our instrument working. And peering deep down inside the instrument, the fuse F1 is that little glass thing right in there. It's going to be difficult to get to, but that's it. And it is indeed open. So that's the defective part, and it looks like that's the only defective part in the entire circuit. So I'm going to jumper that with a wire temporarily and see if I can't order a similar fuse that solders into the main circuit board with the through-hole wire terminals. And in the meantime, I'll have just a wire there instead, and it'll be working just fine. Well, after considerable disassembly, I was finally able to access and desolder the blown fuse, and I was just going to replace it with a piece of wire while the one that I have on order comes in. But I'm not going to do that. I'm going to wait until the new fuse comes in, because it was so difficult removing the entire front panel and all the switch shafts and everything, that I'm not going to stick a wire in there and then come back 3 days later and do that all again just to replace this fuse. So when these fuses come in a couple of days, I'll be back and reinstall a new fuse in the location where the blown one was located, and I'll put this entire instrument back together, and hopefully it will be like new. Hopefully. So I'll be back in a couple of days. All right, so it's a few days later, and the fuses that I ordered have come in. This is what the new fuse looks like. It doesn't look anything like the old fuse. It looks more like a little resistor, but it's not a resistor. It actually is a 62 milliamp fuse. I'm going to drop this new fuse into the circuit board and reassemble the entire oscillator, and we'll try it out. All right, now I have the whole thing put back together, and I'm so confident that it's going to work that I put the top and bottom covers on it and everything. I didn't do any adjustments on the inside. In fact, I'm not even sure that it's going to work yet. I have not turned it on. I can tell you that there's a green LED right here that indicates when you have it turned on, and I broke that LED when I was putting the front cover on. The front panel was, I don't know, the LED's like hardwired back into the main board, and it's kind of tricky, and I messed it all up. So I'm gonna have to get it opened up again and stick another green LED in that spot. But I'm gonna do that off camera at a later date. I'm not gonna do that today. That's a minor thing. So you can't really tell when it's turned on, except whether or not you have output. So I have it wired up with a 600 ohm termination, and the output going through this coax to the input of my scope, which is off screen. I'm ready. Let's turn it on. Moment of truth. Ah, we have a sine wave. All right, let me put the camera on the scope so I can show you what it looks like. Okay, there is 1 kilohertz frequency range, 1 times 100, and the frequency dial 10.0. And should be 3 volts RMS at the output, which would be what, 6 times 2.8, whatever that is. 2, 4, 6, 8, looks like almost 9 volts peak to peak. I guess that's about right. It looks like it's good. I can dial down the amplitude with the amplitude vernier, and that dials just fine. Here, let me adjust my trigger. There we go. We step down in 10 dB steps. Looks like a good sine wave. Let's increase my sensitivity on the scope. Yeah, looks pretty good. Well, it looks like we have a dirty switch contacts on the attenuator. I'll work on that. I should have done that when it was in there, but I can do that. It's very simple, cleaning the switch contacts. You've all seen me do that before. So it's working. Let's try the other ranges. Here's the times 1 kilohertz range. That should be 10 kilohertz. We have is that 10 kilohertz? Looks like it could be 10 kilohertz. Yes, absolutely. That's a 10 kilohertz signal. All right, and 100 kilohertz. Yeah, that's 100 kilohertz. Very good. All right. Let's do 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.1. All of those ranges work. Now the tenths range, let's do the 1.0, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9. All of those ranges work too. Now there's a frequency vernier control. Let me adjust that, see if it makes a change. Oh, this one is also dirty. I'm going to have to clean that pot as well. Yeah, I haven't done that, but I'm going to have to open it up again to take care of those, as well as work on that LED on the front panel. But essentially, it's working. All right, I wanted to hook it up to the 339A distortion analyzer and see if we can measure the distortion. I mean, it looks like a nice clean sine wave, but there should be an extremely clean sine wave, and there's no way to notice that on the scope. So let's hook it up to that distortion analyzer and see what its distortion actually is. I'll be right back when I've done that. All right, so I have a confession to make. It appears that I'm not really able to make a distortion measurement on this 239A. Appears that there might be something still wrong with my 339A or the 3585A spectrum analyzer that's connected to the monitor output of my 339A. But here's what I've done. I've set up the 239A oscillator that I'm testing through this coax cable into a 600 ohm load, into the input of my 339A distortion measurement set. When I make a distortion measurement on the meter, it reads minus 80, minus 10, so negative 90 dB. So the distortion is 90 dB below the fundamental at this 10 kilohertz frequency. So that's what we're set to on the analyzer and on the oscillator is 10 kilohertz frequency. I've tried it also on 1 kilohertz and the same. Now, the meter doesn't necessarily indicate what the distortion is, and that's why we use the spectrum analyzer output through the monitor to take a look at the output of the monitor with the spectrum analyzer. When I do that, I'm not gonna show that to you, but when I do that, the measurement I get is negative 94 dB. Now the spec for the 239 oscillator is negative 95 dB. So it's 1 dB out of spec when I make the actual measurement with the spectrum analyzer. Negative 1 dB. It's 1 dB out of spec. When I switch the input of the distortion measurement set from the 239A oscillator over here to the 339A oscillator, I get the same result, negative 94, when the spec for this oscillator is also negative 95. They're the same oscillator. The oscillator in this instrument and this standalone oscillator are the same circuit exactly. So the specs are exactly the same. So this one also measures 1 dB out of spec. Now that only the only thing I can conclude from that is there is distortion being generated inside the distortion analyzer, or there's distortion being generated in my 3585 spectrum analyzer, which is probably not the case. So there looks like apparently there's still something wrong with my 339A, and I can't really make a measurement because it looks like it's 1 dB out of spec when both of these oscillators measure 1 dB out of spec. I'm sure that they can't both be bad. In fact, I don't think either one of them is bad, but there's something in the analyzer that's still a little bit marginal. And so I won't actually be able to make a distortion measurement on the 239 oscillator. But we are very close. And I'm going to have to just leave it at that because this video is going on way too long already. And I think the oscillator is actually working, but I can't prove it. I just can't prove it. It looks like it's 1 dB out of spec, but I don't think I have enough uh, horsepower in my measurement test setup, and this is the best thing I've got. So I don't have enough. I don't have enough bandwidth I mean, dynamic range to actually make the measurement that I need to make. So that's the 239 oscillator from Hewlett Packard. Yeah, I got it working almost. I still have to replace the LED, the green LED, and I did go back in and clean all the switch contacts so they're no longer noisy. Um, and I think it works, but I can't prove it. I think it meets spec, but I can't prove it. Um, it does meet the frequency specs and it meets amplitude specs, but I can't test it for distortion. I don't have enough power in my equipment, I guess. There might be something still wrong with this guy. I was hoping I had it fixed, but perhaps not. I don't know. Anyway, that will do it for this episode. Thank you very much for watching. Please like and subscribe, and stay tuned for more fun videos with HP vintage test equipment and other fun stuff. I have something new coming up soon that I'm sure you'll really enjoy, so stay tuned for that. Thanks for watching.